Okay, so in this section of the class, we're going to talk about the periodic table of the elements. And this periodic table is going to be a very useful tool for you moving forward. We're going to talk about most of the stuff you can do with it in this section. There's going to be a few things that get added later. So it's going to be kind of like a Swiss Army knife that eventually you're like, oh, wow, like there's a spoon and a knife and a fork. And then later on, you're like, oh, there's like a laser cutter. Like, who knew? Like, it just keeps finding new uses for this tool. So, we're not kidding when you say it'll be your new best friend. It's going to be incredibly helpful. If you are able to print out a copy, I highly recommend it to help you out with exams and stuff. Um, and when you're working on the homework and things like that. But if not, you can always just use a digital copy. That's fine. And either way, we have it on the Moodle page. And so it's going to be in the course info section because it's just a general course resource. So we've got our periodic table of the elements right here. So when you open it up, you get this guy right here. And how do you know it's periodic table of the elements? Because we label it the periodic table of the elements. And so there's 118 elements that we know about currently. We could add more once we find them, once we discover them. Or generally at this point, we're actually making them in labs and observing them for the smallest, faintest fraction of a second and be like, aha, yes, now the world has muscovium, yes, yes, and livermorium, and tennessine in it. It should have been tennesseum. I don't know what they're doing. Tennessine in it, whatever that is. And oganesson, because everyone will know the name of oganesson. All right, so these are all man-made down here. And so they observe they're not stable. They fall apart very quickly. It's like when you're a kid. You guys are all probably too young to have ever used wooden blocks because you didn't grow up in the land of fire being a technology, cutting edge technology. But you stack them and they fall over. If it gets too tall, like that's what's happening here. These nuclei start getting too big. They fall apart too easily. Now the interesting thing is if we start discovering a few more, theoretically, there's a model showing that those nuclei are going to be stable again. So there's an island of stability. So they could actually stick around for a while. Maybe we could do some cool stuff with them. Who knows? All right, so let's kind of break this down. So I started at the end. Let's actually move back to the beginning here. So the way we use the periodic table, we read it left to right, and then we go down a line left to right, and we jump the gaps. So this is just like we read, a piece of paper. We go across left to right, and then we go to the next line left to right, and we do ignore these gaps. So just a heads up on that. Now within each of these cells, there is a key here to help you remember what's what, but there's essentially 4 pieces of information. There's technically this 5th one that tells you the phase, but whatever. Phase at room temperature and pressure. Cloud means gas. That means a solid little cube, and then liquid is a drop. So like mercury and bromine are liquids. I think they're the only ones on the periodic table, if I remember right. Most everything else is a solid. Few gases over here. Okay, so there's that little piece of information that's not super helpful for this class. There's not really much we're going to be doing with that. But we have this number in the top left. That's the atomic number. That's a very helpful piece of information we'll talk about in a little bit. And you'll notice that we're organized atomic number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this periodic table is organized in order of increasing atomic number. So every element is an atomic number that is 1 larger than the previous. I can go anywhere. I can point here. We look at silver, it has atomic number 47. Well, palladium was the element before it, atomic number 46. After silver, atomic number 48, and we call that cadmium. So every element also has a chemical symbol and a name. And so there's, every element has a name. Otherwise, how would we talk about stuff? Be like, no, the brown element. Well, which one's the brown element? Well, it's probably bromine. But anyway, it gets a little bit weird when you're like the metallic looking element. And it's like, oh, you mean one of the metals that are the majority of these? So they have names. And then because we're lazy, I'm just going to say it, chemists are lazy. For every name, there's a chemical symbol that is 1, 2 letters max. If we really have to, we'll use 2 letters, but we really don't want it. So for example, carbon is a C. When we get to calcium, C is already taken, so we go Ca. And the second letter is always lowercase, so it's capital and then lowercase if there is a second letter. And then the 4th piece of information is the atomic weight. And so that is the average weight of, say, a carbon atom on Earth. And so this is an AMUs. And so the average carbon atom, average. So this is all of, if we took all of the carbons on Earth and found and averaged the weight between them, it's 12.01. So it's not saying that a carbon atom is 12.01. It's just that on average, a carbon atom is 12.01. Now remember that protons and neutrons are in the nucleus. They each have a mass of about 1 AMU. So how do we start knowing, how that breaks down? So it's like, well, there's 12, and I'm just going to round it to the nearest 1 for the most common isotope. So generally carbon is 12. The atomic number of 6 isn't just helping us with organization, but that's how many protons the nucleus has. So all hydrogen atoms have 1 proton. All helium atoms have 2 protons. And all carbon atoms have 6. Where did I go to before? Silver. All silver atoms, 47 protons. All oganesson, I guess that's oganesson? Oganesson, I'm going to say it like that. 118 protons in the nucleus. So it starts stacking up when you get down here. So if we look back at carbon here, 6 protons. If it has a mass of 12, electrons aren't really contributing to the mass at all, so we don't worry about those. But 6 plus the number of neutrons equals the mass, so it's going to have 6 protons, 6 neutrons to give us a mass of 12. That's going to be the most common isotope of carbon. So carbon 12 is the most common isotope. Now about 1 in 100 are carbon 13, so that's going to bump our average up a little bit when we average that in. And about 1 in 1,000 are carbon 14, and so that's going to bump our average up a little bit as well. And so that's why it's not exactly 12, because not all carbon atoms are carbon 12. Only like, what is it, 9,998 out of 1,000 or something, or out of 10,000 or something like that are carbon. So the vast majority of them are carbon 12. But occasionally there's one that isn't. And so it sneaks that average up a little bit. And I never go past the hundredths place when I talk about the atomic weight. I just round it. So like hydrogen here, whoops, you can click on it. Oh, it's clickable. That doesn't happen when it's on paper. Anyway, hydrogen is 1.01 AMU. That's what I say. Boron, 10.81. Carbon, 12.01. I don't worry about that extra 1. And if you have something like, technetium here and it says 98 and it's in brackets like that, it means that they've only observed technetium 98 because it's radioactive. There's only one, it's only there for a brief moment and it falls apart. So, there's a few larger details to the periodic table as well. So first is just, how to use these cells, what information they give you. And we're going to talk more about the atomic weight, atomic number stuff. But do be aware at least of the atomic number right off the bat. So we are organizing an increasing number of protons. Be another way of talking about this. So every element has 1 more proton than the last. And the chemical symbols tend to go with the elements pretty well. Like, vanadium's a V, titanium Ti. Okay, cool. Calcium Ca because carbon was already C. But there's some weird ones. Sodium, Na. How do you spell sodium with an Na? Like, what's going on there? Potassium K? Like, what? What is that, Silver, Ag. Gold, Au. Lead, Pb. Iron. There's iron. Fe. Like, what's going on here? What is this? What is this? Copper, Cu. Well, the answer, like most of the problems in the world today, it all dates back to the Roman Empire. So those chemical symbols are built off of the Latin names. So Romans knew about sodium. They called it natrium. Romans knew about tungsten, but they called it wolfram. So it gets a W. Gold was aurum because, like an aura. Silver was, I don't know what silver was. Lead, that's my favorite one though. Lead, Pb for plumbum because they used it for their plumbing. That's a fact. That's true. Some things never change. Turns out the Romans were hired to build all of the plumbing for Flint, Michigan. Who knew? So, and they had the same problems that we do with using lead for plumbing. They just didn't know it. In fact, they would do this one thing where If you boil water and you throw lead in it, the water tastes sweet. They were literally drinking lead water, and because it tasted good. So when people are like talking about all the reasons the Roman Empire collapsed, I feel like lead could get a little bit more mention in there. All right, so we're gonna kind of zoom out from the individual squares now. So like there's the piece of information that are in each square. The position on the periodic table is also going to give us information, and we're going to talk in more detail about that in subsequent videos. But right off the bat, there's some big breaks I want to talk about here. So the first one is metals. You're either a metal or you're not, right? You're a non-metal or a metal. So the metals, so hydrogen's over here, it's not a metal. You'll notice there's a strong black line here. Inside of this line are all the metals, this thick line. Over here, we have nonmetals. Hydrogen's a nonmetal, but it is spying on the metals. Its job, it's the mole. It's keeping an eye, making sure they're not conspiring against the nonmetals. And then within the metals, there's a couple of groups. So, from lithium on down, we call these alkali metals. This isn't super important, just a heads up. Like, the naming can go and go and go. We have alkaline earth metals. And then in the middle here, this chunk of metals, we call these the transition metals. And then this is the lanthanide series and the actinide series. And one thing I want to point out with this that I haven't yet is notice this is 57 to 71. And so this row right here isn't below the 118. It's actually between barium and hafnium, so it fits in here. Now the reason we do this is just so we don't have some awful scaling issues where this periodic table it gets wider than it does taller. It just keeps getting wider and wider and wider. So to make it fit on a piece of paper nicely, sometimes there's a little illustration that shows like something that shows that this goes here. But just pay attention to the numbers. So it goes 55, 56. It doesn't just magically jump to 72. It goes 56, down here 57, 8, 9, 10, blah, blah, blah. 71, comes back 72. And so same thing with the actinide series right here. It's going to go 88, 89, 90, blah, 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 103, and it's going to come back 104, good old Rutherfordium, named after the guy that discovered that the atom has a nucleus. Or rather, he came up with the experiment, and then a student ran the experiment and discovered it. There are no elements on the periodic table named after that student. Welcome to the world of science. The professor gets the name. All right. So yeah, be aware that there's a little bit of formatting stuff, and that just has to do with the restrictions of the dimensions of a piece of paper. So we got transition metals over here, and then it gets kind of metalloids in here, are what we call these. So a little fuzzy between transition metals and metalloids, but don't worry about it too much. And then within the nonmetals, there's kind of two major groups. There's the halides, fluorine, chlorine, bromine, iodine, astenine. These are called halides or halogens. Two names are used kind of interchangeably. And then on the very end, we're going to talk more about these in the next video or two, are the noble gases. These are the halves of the periodic table. We'll talk about why that is. But that's why they're called the noble. They're so noble, these gases. And if these are the halves, like this is, the rich suburb of the periodic table, this is kind of like, all the other neighborhoods. Boron is the most unfortunate element in the periodic table. Like, this is like Sesame Street, and then I don't know what this is, like Sesame Falls outside of Sesame Street where they have like the private golf course and everything, tennis club. Boron's Oscar the Grouch, living in the trash can. Everyone's like, "Why are you so mad, Boron?" And Boron's like, I live in a trash can. What do you expect me to like? I'm supposed to be good with that? Like, come on, you got to help me out a little bit." And then these guys over here are just too busy playing tennis to even know. And Carvin's like, "God, I wish Boron would go another street. I'm kind of tired of dealing with Boron by my front step all the time." Anyway, that's kind of everything with the periodic table there. I will never pass up an opportunity to make fun of Boron. Or point out, I'm sorry, not make fun of Boron. Raise awareness of Boron's plight in the world today. All right, so we're going to kind of build off this. This is going to be a tool that we use. This information of the cells is going to be important. And then, oh, I almost forgot. Why is it called the periodic table of elements? Well, another name for the rows, I'm always just going to say rows and columns. But rows are also called periods. So you move across a period. Well, and then the columns are also called groups. And the reason they have these names is you tend to get similar chemical behavior among a group. So all the noble gases have similar chemical behavior, which is essentially none. They don't need any friends. Uh, Fluorine, chlorine, bromine, iodine, acidine, they tend to behave very similar chemically. Same with like lithium, sodium, potassium, rubidium, cesium, francium, the alkali metals will all behave similarly. Alkaline earth metals here will behave similarly, so beryllium, magnesium, calcium, strontium, barium, and then radium has some other issues going on. But if it can hold itself together, it chemically will behave the same. Nuclear processes are different. It will fall apart at the nucleus because it's unstable and release radiation. Um, and so that's why they're called groups, and that's why you'll notice like this was a name, this was a name, and then these behave very differently, but it's just kind of a group. And then this had its own name, this had its own name. It's because they behave very similarly. And then these, we'll get into more detail about like what the position of these mean. Some details there, and I think that's a good introduction for the periodic table. And we'll start to use it for different things. I'll show you how to use this tool a little bit more. So right now you should be able to know how many protons are in an element. An element is defined by its number of protons. What number is that? Like beryllium, how many protons does beryllium have? 4. And then you can find the atomic weight, chemical symbol, and the name. That's where we are right now. And we'll get into more detail. There's going to be some important details about metals versus nonmetals that we'll talk about, but that'll actually be in another section. And we'll start talking about, like I said, the specific position on the periodic table and how that helps us out. And that'll be the next video or two. So, again, this is going to be your friend. There's going to be a lot you can do with this. This is all information you don't have to memorize. You'll always have access to a periodic table. You don't need to memorize chemical symbols or names. Or, that boron has 5 protons and infinite misfortune. None of that. You don't have to memorize anything. You just look at the periodic table and it will tell you. So, we'll leave it there and then we'll pick it up with some other videos. The last thing I'll say is I will continue to use this microphone for my videos moving forward. I noticed that my DocuCam microphone was pretty faint, so I apologize for those first couple sections if you had to really crank the volume, and then later on you went to something else and then blew out an eardrum. I apologize. I'll make sure to use this microphone from now on. So, like I said, if you can print this, great. If not, that's cool. You can just keep a digital copy. If you have something with a touch screen, you can make notes on it or whatever. That's fine. All right. So on to more information about periodic table.